So we started talking about the idea that it's important for us to understand that while PV equals nRT is nice because it describes the behavior of particles, and we can do a lot of stuff with it, and it helped us figure out a lot of things about a lot of chemical reactions. And we need to know about all that stuff. We also need to understand why this works, okay? So, and this is the way that science works again. We make observations, and then we create a mathematical law that describes these creations, these observations, but the mathematical law is just a mathematical law. It just says this is the math that explains our observations, but it doesn't say why. And then we go and figure out why this mathematical law works. And in this case, it's because we can relate the temperature of the gas laws to the kinetic energy. And we said that the let's see, which one of these do we want? We said that the kinetic energy, the average kinetic energy, equals 3/2 times the gas law constant times the temperature. So we can relate all of the things regarding the gas laws to something about the energy. We've said, how does the kinetic molecular theory explain this relationship? How does it explain this relationship? How does it explain this relationship and this relationship and this relationship? So mostly you have to understand the concepts of it. How does the kinetic molecular theory explain it? But you do also have to understand this relationship here where we have the gas law, PV over N equals RT, right? And we've just rearranged the gas law a little bit. We've put N on one side and RT is still over here. But this is going to equal 2/3 times the kinetic energy. Or I can rearrange that to say that the kinetic energy equals 3/2 RT. And again, I forget which one. It's either this relationship or this relationship that's given to you on the formula sheet on the AP test. But we have to be aware of that, and we also have to be aware that from that, because we know that kinetic energy relates to velocity, we can actually figure out what the velocity of particles are, and we have this relationship here that states that the root mean square velocity of a group of particles equals the square root of 3RT over Avogadro's number times the mass of one particle, or 3RT over the molar mass. And we recognized that we needed a different constant for that as well, joules per mole Kelvin, as opposed to liter atmospheres per mole Kelvin. Although we recognize that if we look at the actual units involved in liter atmospheres, that works out to be the same thing as joules. But it's a different value because we're using different things. And so we calculated the velocity for atoms of helium gas. And then we also talked about the need to be able to do that for one particle using the Boltzmann constant. And so we found out what the root mean speed of individual particles of these gases were at those temperatures as well. And the reason that we want to study this is because it helps us understand the nature of chemical reactions a little bit more. And we'll connect this later on to the kinetics of chemical reactions. But right now, we just kind of need to understand this idea of a distribution of speeds of particles. And so we've got the speed of the particles on the bottom here, and then we've got the number of particles with a certain speed on the y-axis here. And so at certain temperatures for individual substances, we can create a distribution here where we can figure out or visualize what the speeds of particles are in a given sample of gas at different temperatures. And as we increase the temperature, we can see that the speed, the most probable speed increases, right? That's one thing that we can see. The most probable speed increases with temperature. The other thing that we can see is that as I increase the temperature, my distribution broadens out a great deal. Okay? Since I have more speeds that I could be at, I'm going to have fewer particles at each individual speed. And we also notice that this skews a little bit to the right. Okay, and we're going to talk about that. So the above graph shows us the number of particles at a range of speeds in meters per second for nitrogen molecules. The distribution at each temperature centers around a central value of speed, which is the greatest number of where the greatest number of particles are at. That's called the mode. And I don't know if you're familiar with the difference between the mode and the mean. The mean is just the average velocity, right? But the mode is the number of particles that the greatest number of particles for a given distribution or a point in the distribution. So at the mode, that's the point where I have the greatest number of particles. And that might not be the same thing as the mean. The average value, because I am skewed to the right a little bit, the average value is going to be a little bit to the right of that. Okay? So the distribution is skewed to the right. That is, the tail of the distribution is longer on the right side of the graph. This is also called a positive skew. In this instance, this is because there's a confining boundary on the left side of the distribution. I can't go slower than 0 meters per second, right? But I can continue to go greater and greater speeds, and that's going to cause the distribution to skew to the right. However, at the right side of the distribution, there will always be a few particles that have higher velocities. As temperatures become greater, the range of speeds increases, so the number of particles at each speed becomes fewer, and the graph flattens out. As temperatures become greater, the most probable speed increases. This reflects the fact that as the temperature increases, the particles attain greater kinetic energy. And we remember at a given temperature, the particles of all gases have the same average kinetic energy, which is not the same thing as the most probable speed. So the average speed is going to be greater than the most probable speed. So what we're going to find out is that for chemical reactions, only a certain proportion of the distribution will have adequate energy to initiate chemical reactions. Okay? So it may be that when we talk about this, you may think, well, if I have a bunch of nitrogen here and I have something that nitrogen can react with, all of these particles are available to react with all of the other particles of whatever it is that they're reacting with. The fact of the matter is that when first of all, I have to collide with something in order to react, right? We talked about that. If I have a particle here and a particle here, if they're sitting on a piece of wood, they're not going to ever react, right? Right. So, but if they're moving in the same space, they can smack each other, and that's the point at which they can react. But we also said they have to have a certain amount of kinetic energy to react. And what we're going to find out is that only a proportion of these things are going to have the ability to react. So at this temperature, only these particles may have the ability, the kinetic energy, to actually cause a reaction. But at this temperature, I'm going to have enough kinetic energy so that all of these particles have the ability to react. And then at this even higher temperature, I'm going to have the ability for all of these particles to react. But I'm still not going to have the ability for these particles to react because they can't smack the other particles with enough kinetic energy to actually cause the reaction to occur. And what we're going to find out is that, for example, if I have a hydrogen atom here, okay, and it's going to, or actually an oxygen atom, and let's say that this is a hydrogen molecule here. If I have an oxygen atom that's free and it wants to interact with these two, hopefully it makes sense that in order to get this free oxygen atom, I've had to, oops, I don't want to do that. I've had to separate two oxygen atoms from the double bond there. In order for one of these oxygen atoms to be able to interact with these two hydrogen atoms, I've had to do this to begin with, okay? And that's going to require some energy for me to cause that to happen. And then I'm going to have to smack right there, okay? If the oxygen atom smacks the particle this way, they're not going to react, right? I have to apply this energy here to the middle of this bond in order for them to be able to actually form this molecule, okay? And so what we're going to find out is that part of this process of reaction and how fast something reacts is going to be related to the fact that not only do I have to hit the other molecule, not only do I have to hit it with enough kinetic energy in order to break this bond and then allow these two new bonds to be formed, right? When this oxygen hits this molecule, it's going to have to cause these hydrogens to come apart. Not only do I have to have it hit with that much energy, I'm also going to have it hit with the right orientation. So these are all factors that go into how fast will a chemical reaction occur, or will it even occur at all. If none of these oxygen atoms are at the right energy, then they're not going to react even a little bit. Okay, so this becomes really important in determining whether or not a reaction occurs. But we'll talk about that when we talk about the kinetics of chemical reactions. Okay, so that's why we're addressing it here, though. So at a given temperature, the particles of all gases have the same average kinetic energy, and we'll find out that for chemical reactions, only a certain proportion of the distribution will have enough energy to initiate chemical reactions. We can also characterize the nature of collisions in a sample of particles. The vast number of collisions is what gives rise to the distribution of velocities, right? If all of these particles were flying in the same direction, okay, and they all had the same, and the average kinetic energy was the same for these particles as it was for another group of particles, but they were all flying in the same direction, there wouldn't be any reason for them to have a distribution of velocities. They'd all just simply have the same velocity. But these particles are all smacking into each other, and as they smack into each other, their velocities change. And so the number of collisions is what gives rise to this vast number of velocities. Okay. The distance between collisions is called the mean free path. Okay. And the distance between collisions is on the order of 10 to the negative 7th meters for small molecules. In other words, I travel about a billionth of a meter before I smack into another particle. Okay? The number of collisions is also related to rates of chemical reactions. And we'll talk more about this idea of the mean free path when we talk about chemical reactions. Now, this gives rise to some additional properties of gases that we need to think about. So if we look at this diagram here, we have a container with gas on the left side, and let's say we had initially have a vacuum on the right side, and the container is separated by a plate with pinhole in it, and the pinhole will allow small particles through it. Very small particles, obviously particles of gas. And recognize that a vacuum is simply the absence of particles of gas, right? We have no gas particles in a place with a vacuum, and that means that there's no pressure there, right? And so since there's no pressure in there, there's going to be a pressure gradient that's going to try and push particles through that hole there. Okay, and so we have this plate with a small hole where gas particles can escape into this vacuum. And the movement of gas particles into a vacuum is called effusion. And that's different than diffusion. Okay, that's different than diffusion. Diffusion is where particles move through other gas particles. Effusion is where particles move into a vacuum. In 1846, chemist Thomas Graham found that the rate of effusion is inversely proportional to the square root of the density of the gas. And so also it's inversely related to the molar mass. Okay, and remember this is our symbol for the mass of 1 mole in kilograms per mole. Remember back up here, we said we use the big M to indicate molar mass in kilograms per mole rather than in grams per mole. Okay, so hopefully it makes sense that the greater the mass I have, the slower I'm going to effuse into a vacuum. The greater the mass I have, the slower I'm going to effuse into a vacuum. Okay, and the kinetic molecular theory basis for this is the understanding that particles with less molar mass have greater average velocities. Right? Again, if I have 22.4 liters of gas at standard temperature and pressure, I have 1 mole of gas. Right? But if I have hydrogen particles and I have 1 mole of oxygen particles, which will also take up 22.4 liters. Remember, this is the standard molar volume at standard temperature and pressure. It doesn't matter what type of particle I have, 1 mole of gas will take up the same volume. right? And we said that that was because of this relationship of kinetic energy, or 1/2 mv squared. If I have a greater mass, and oxygen is going to have a greater mass, I have a lesser volume. So if I increase the mass, or I have not a volume, I'm going to decrease the velocity, right? If I increase the mass, I'm going to decrease the velocity. And that's the kinetic molecular theory basis for this understanding. Things with lesser molar mass has greater velocity. Therefore, if I have a lesser molar mass, I'm going to have a greater rate of effusion. If I have a greater molar mass, I'm going to have a lesser rate of effusion. And the thing that we can do is that we can compare experimentally the rates of effusion of gases. Okay, so if I say that the ratio of effusion for gas 1 to gas 2 is something, then the ratio of the square roots of their molar masses is going to be the inverse of that. And hopefully you can see that if I have an unknown gas, if I have a gas with an unknown molecular mass, and I don't know much about that gas, if I have a gas with an unknown mass, I can compare its effusion to the effusion of a known gas. So let's say that this gas was something that I knew about. Let's say it's just hydrogen, and then I have this gas that I don't know about. Okay, I can compare its rate of effusion, and whatever that rate of effusion is, I can see that the inverse of that, I'll know this molar mass, I'll be able to find this molar mass by isolating it and multiplying this ratio times the molar mass of the one thing, or the square root of the molar mass. Okay, so if I have a mixture of helium and methane, and they're placed in an effusion apparatus, I should be able to figure out what the ratio of their effusion rates is. Okay, I can figure out what the ratio of their effusion rates is going to be by plugging values into their molar mass. So let's try that. So effusion for helium and effusion for methane is going to equal the square root of, and the molar mass of methane is going to be 12.01 plus 4.04, right? 12.01 for carbon, 4 times 1.01 for hydrogen, so 16.05. So it's going to be 16.05, and I'm going to need to do this to the ratios are still going to be the same, I guess. So the square root of that divided by the square root, and helium is 4.003, so 0.00403. So you can say square root of 0.01605 divided by square root of 0.04003. Okay, so what I find out then is that and in hindsight this should make sense, that the rate of the fusion from helium to methane should be about 2. Okay? So what is the ratio of the molar mass of this to this? Just the plain molar mass, not the square roots. 16 compared to 4 is 4 times, right? So what's the square root of that? 2. Okay? So since helium has 1/4 of the molar mass of methane, it will effuse at twice the rate of methane. Okay? Since it has 1/4 of the mass, it will effuse at twice the rate. It'll move twice as fast. Now, this is just a sideline. This is just a piece of interesting information. An important application is of Graham's laws in the separation of gaseous substances. Okay? Hopefully it makes sense that if I have a mixture of gaseous substances, they're going to effuse at different rates, and I can use that to help separate them, especially those that have similar chemical properties. Consider uranium. There are 2 main isotopes, uranium-235 and uranium-238, and I would not be able to separate those in any way chemically. There's no chemical way that I could separate them based on their molar mass. They're the same compound, right? They just have a different number of neutrons. All isotopes of uranium undergo radioactive decay, but only one, uranium-235, can sustain a nuclear reaction in a nuclear reactor. The sustaining of a nuclear reaction depends on the number of particles released in the radioactive decay process that can then bombard additional nuclei and so on. In order for enough particles to be generated to sustain a nuclear reaction, a mixture of uranium has to be at least 3 to 5% uranium-235. So I have to have at least 3 to 5% of this isotope in a mixture of uranium in order for it to be able to sustain a nuclear reaction. Unfortunately, 99.3% of naturally occurring uranium is the wrong kind. Only 0.7% is 235. So, as there are no chemical differences between the two, it would be exceedingly difficult to separate them. So any enrichment process that needs to take advantage of this, needs to take advantage of the slight difference in atomic mass. The accomplishment of this enrichment, so you've probably heard of we have to enrich uranium in order to make it so that we can use it in nuclear reactors or in nuclear weapons. And this is what the controversy related to Iran is all about. We can react uranium ore with fluorine to create gases with uranium of uranium-235 and 238. Then we can pass the gas mixture through a series of chambers separated by porous plates. This is the process of effusion, right? And this one should effuse faster because it has lower molar mass, right? And this one should effuse slower. The uranium-235 will move through the chambers this amount faster than the uranium-238 will. There's something that we've created called a gas centrifuge that's basically the same process in a much more rapid form. And this is the procedure that's used today. But one of the controversies related to Iran is that and I'm not trying to be political here in any way, shape, or form. I'm just pointing out a thing here that shows the utility of this technique. The controversy with Iran is that we wanted them to destroy a bunch of their gas centrifuges. And that was part of the peace process or whatever it was, the nuclear accord with them. But that's the controversy, and this is one of the utilities of this kind of a Graham's law kind of thing. So anyway, again, it's not to be political, it's just to show you that this is a very, very useful process, and it has global implications. Does that make sense? Okay, so this is effusion. Diffusion is the movement of one substance through another substance, and it follows the same law. As substances with lower molar masses will have greater average speed and will effuse faster, they will also diffuse more quickly, and the relationship between the rate of diffusion and the square root of the molar mass is the same as it was for the rate of effusion. Okay, so the rate of diffusion of a substance is proportional or inversely proportional to wow, that's not confusing at all, is it? The rate of diffusion is proportional to, yeah, I'm not sure why this is here. This shouldn't be here. So the rate of diffusion is proportional, inversely proportional to the square root of the molar mass. Okay, so I have no idea why that's there, and in fact, I'm just going to get rid of that right now. Why? Therefore, the ratio of the two gases diffusing through another gas or a mixture of gases will also show the same relationship as we saw for effusion. Okay, we typically compare rates of diffusion of two substances in air. How fast does one substance diffuse through air versus another? And this is kind of an interesting thing. How soon is it once someone releases some kind of a scent, a perfume or something into the air in a room, how soon is it before you notice that?
Well, it depends how strong it is.
It does, but it's usually pretty quick, right? If somebody uses a can of Axe on themselves, how soon is it before you know they walked into the room? It's usually pretty quickly.
Before they walk in the room.
Even before they're in the room, yeah.
Depending how much they put on.
Yeah. Well, I've said they use the whole can.
Oh, okay, yeah, definitely before the room.
Which is typical of male teenagers. Anyway, rates of diffusion are slower than rates of effusion due to the large number of collisions, right? But it's still the same process, basically. Gases also diffuse through liquids and solids as well. Consider diffusion of oxygen in the bloodstream. I have to have oxygen be able to diffuse into my red blood cells, right? Or there's oxygen that diffuses through pond water so that the fish can get it. So we talked about the idea of the average, the mean free path, the average distance a particle can move before it collides with another particle is called the mean free path. And the value of this depends on the diameter of the particle, right? Obviously, if I've got a tiny particle, it's going to be able to move further before it smacks something, right? It's going to be able to move further before it smacks something than a bigger particle. The collision frequency can then be determined by dividing the most probable speed of a population by the mean free path. In other words, I can divide whatever that speed is, let's say it's 1,000 meters per second, by the mean free path, how far it goes before it collides with something. And if I do that, that's going to give me the time it takes for me to smack into something. And in general, for a mole of gas at standard temperature and pressure, there are billions of collisions per second. So on one hand, when you talk about chemical reactions taking place, and we need to know how fast it is so we can tell if it's going to hit the other particle with enough speed, you start to think, well, how do reactions ever occur? Because maybe I don't have a lot of particles that are at the right speed. But you have to realize that we're at billions of collisions per second, okay? With 1 mole of gas, we're smacking billions and billions of times per second. So even if I only have a tiny part of this distribution where I've got the right speed to create a reaction, if I've got billions of collisions per second, the chances are still good I'm going to have enough of these particles that are smacking each other that we're going to have things reacting. Okay, so we'll talk a lot more about those ideas when we talk about rate kinetics. How fast does a reaction occur? But we introduce it here in gas laws because that's where it most naturally fits. Okay, so we'll bring that back later on, and we'll be able to review those concepts a little bit in case they're not entirely clear right now. Okay, now one last thing that we need to talk about related to gas laws is that we've pretended like this is the way it is for everything. The ideal gas law is in effect, and it's the only thing that's in effect, but that's not true. We deviate from the ideal gas law, and we need to know something about why that happens. So we've made a big deal out of the fact that the ideal gas laws work because there are no attractive forces between particles, and when particles collide, energy is transferred between them elastically without being lost. So now we have to hang our heads and say, you know, it's actually kind of a lie. It's only mostly true. It's like being mostly dead, but not. All right, okay, never mind. Princess Bride, right?
Yeah.
Okay. Okay, but especially in extremes of temperatures, gas particles deviate from the behavior we see closer to standard conditions. At extremes of temperatures, gas particles deviate from the behavior we see closer to standard conditions. In particular, there are two parts of the kinetic molecular theory that, while they are useful approximations, they don't always reflect reality, and we can get into trouble if we're not aware of these issues. Now, I apologize for the issues with the video here, or the technology. It's partly because my computer is starting to run out of space, and I need to do something to change that. Did that happen last time too? Maybe that was with a different class.
It happened a little bit. But not
Okay.
a lot.
Anyway, points of possible deviation. Okay, so postulate one of the kinetic molecular theory says that as the particles of gas make up so little of the volume present, they can be considered simply to be points that have no volume. Okay, so if I'm going to say that PV equals nRT, and I'm going to use that to talk about the volume of a gas. Hopefully it makes sense that I need to be able to say that the particles themselves don't take up a lot of volume. But what if particles of gas actually took up, if they were compressed, if the particles of gas actually took up half of the volume present in the space. Okay? What if all of the particles that were compressed together actually took up half of the volume that we were talking about? Okay? That would be a huge problem, wouldn't it? I couldn't then say that this was true. I would have to say this volume is going to change or be affected by how much space these things took up. Okay? But if there were enough circumstances where this wasn't the case, then I can still use it during those circumstances. But if there are circumstances where this volume of particles actually is going to be a problem, I need to know about those problems, okay? Or I need to know about those particles. We know that these particles do in fact have a volume, but we pretend that they don't have a volume, okay? So we've got a little bit of a clue up above where we've said we have to say this is mostly true, especially at the extremes of temperatures. Okay? And what extreme of temperature would cause a problem for these particles? Where would I run into a problem with the number of particles taking up too much volume? At high temperatures or low temperatures?
High, right? It's going to be more spread out and moving faster.
But that's what you actually want. You want them to be more spread out.
Oh, okay.
So at low temperatures, these particles are going to be closer together, right? They almost might be liquid or they almost might be solid if they're even close. But at that point, they're going to start, your volume is going to start coming into play. So at low temperatures and at high pressures, okay, if we were at high pressures, these would actually start to, the volume would start to become a problem. Okay, and we'll talk more about that in just a second. Attractive forces are also a problem. Postulate 3 says we consider there to be no attractive or repulsive forces between the gas. If there were, gases would not behave in the way they do. However, there are attractive and repulsive forces between particles. It's just that near standard conditions, these are not strong enough to significantly affect the behavior of the gases. But if I slow the particles down enough, those attractive forces are actually going to start to come into play. And the motion of this particle will now affect the motion of this particle because it exerts an attractive force on it. Okay? It's going to change the amount of pressure this particle can have. It's going to change the velocity that that particle has without actually contacting it or smacking it. And so under what conditions? Again, if I slow the temperature down, or if I lower the temperature, that's going to slow these particles down. And now as they're approaching each other more slowly, those attractive forces are going to be able to come into play. Even at standard temperature and gases, or standard temperature and pressure, gases deviate slightly. This is not in your book. But gases deviate slightly from standard behavior. Remember, we've said that the volume of 1 mole of gas at standard temperature and pressure is 22.414 liters. Okay? But if I look at these other gases here, I find out that 1 mole of gas of carbon monoxide only takes up 22.388 liters. It takes up less space. 1 mole of ammonia takes up even less space, 22.079 liters. On the other hand, helium takes up a little bit more space. It spreads out more. Hydrogen spreads out more. And what do you notice about the boiling temperature? What do you notice about the boiling temperature here of these as we look at the volumes that they take up?
The larger the volume, or like the greater the volume, the higher the boiling point.
The higher the boiling point, or the
Oh, is that, oh, that's negative.
there's negative, right?
Oh, I didn't see that at first. So
Okay,
that's
yeah.
the lower than the, the colder the, like,
What's absolute zero? Negative what? Yeah, negative 273, because 0 degrees Kelvin is
right.
273 degrees Celsius, right? Okay, so the boiling point, this just blows me away. The boiling point of helium is almost absolute zero, okay? Helium is almost impossible to turn into a liquid because it would turn into a liquid at negative 268.9 degrees.
They have to stay at that heat.
Yeah, and so it would take so much energy to keep it at that temperature. I mean, you would not ever really want to do that because of the outlay of energy that it would take to accomplish that. But notice that this boiling temperature, the lower the boiling temperature, the greater the molar volume. What do you think the boiling temperature is reflecting here? What do you think the boiling temperature reflects? The higher the boiling temperature, the what related to interparticle forces? The higher the boiling temperature, the greater or less the interparticle forces?
Less.
Think about it again. If it takes me more energy to, if it takes me more energy to boil something, then its interparticle forces must also be stronger, right? Okay? The less energy it takes to boil something, the weaker the interparticle forces. So see how this relates to the molar volume. The stronger the interparticle forces, as indicated by the boiling point, the lower the standard molar volume. Okay? That makes sense, right? Because these things have greater interparticle forces, they're not going to have as great a volume at standard temperature and pressure. Okay? So the greater the interparticle forces between these molecules or between these particles, the less the molar volume. The weaker these interparticle forces are, the greater the molar volume. And the AP test loves to have you interpret graphs or lists like this, okay, or tables like this. Okay, so a really, really likely, high likelihood question is you're going to get a table like this and be asked about what does this say about the strength of interparticle forces of such and such, or they'll ask you to compare the strength of the interparticle forces between particles of carbon monoxide and particles of neon. And you would say this table indicates that interparticle forces are stronger between carbon monoxide than they are between neon. Okay? So this is a high likelihood question here. Okay? So anyway, at standard temperature and pressure, even gases or most gases deviate slightly. What aspect of causes of deviation does the boiling point address? And that addresses interparticle forces, right? And remember, interparticle forces relate to physical properties, not chemical properties, right? All I'm doing is changing the state. I'm going from one state to another. I'm not changing the chemical nature of these things at all. Intraparticle forces relate to chemical properties. If I break intraparticle forces, I change the chemical properties. If I break interparticle forces, I change the physical properties. Okay, what factors pertaining to individual gases will affect whether there are significant interparticle forces? Okay, what factors pertaining to individual gases will affect whether there are significant interparticle forces? And what substance do we know that is our model for interparticle forces? Right? What kind of a bond is this? What kind of interparticle force is this?
It's like the gentler force of magnetic force, isn't it?
Not magnetic,
It's like
electrical.
a gentler version of that. Is it polarity?
Okay, but it's a hydrogen bond, right?
Oh.
That's what I'm looking for. Water particles here have hydrogen bonds because they're polar. I have negative influence here, I have positive influence here, and the positive part of the water molecule is going to attract the negative part of the adjacent water molecule, and that's an interparticle force. We're going to learn that these are called dipole forces. What's a dipole? What's di refer to?
It's pulling to it.
What's di? Okay, two. It refers to two. What's pole refer to? It's like the poles of a battery, right? I have a positive charge and a negative charge. Okay, this is a dipole. It's got two poles. That's the only. It's not any fancy word that's got some mysterious meaning. It is exactly what it says it is. It's a dipole. There are two poles. There are two poles to the water molecule, right? I have a, oops, I drew that backwards. If I were to diagram the direction of the positive and negative forces here, or charges here, they would be equally separated. The positive forces are right there, right? They're at this end, and the negative forces are right there. So this arrow indicates the direction of the dipole. The little crosshatch here looks like a positive sign. This is where the positive part of the dipole is, and then the arrow points towards the negative end of the molecule. And these are called dipole forces because they're forces of attraction between dipoles. The water molecule is a dipole. Okay? This is a dipole, this is a dipole, and this is a force of attraction between the two dipoles. And water molecules are not the only thing that do this. Now, this is called a hydrogen bond because it's got an unequal electron distribution that's causing this, right? All of the electrons are hanging out around the oxygen, and when I have a situation where I've got a polar molecule and hydrogen is going to be attracted to that negative part there, we call that a hydrogen bond. Okay? There are other things other than water molecules that can create hydrogen bonds. Okay? And ammonia is a good example. That's right down here ammonia has this structure, NH3, and it acts just like water does. All of the negative charge hangs out around the nitrogen atom. This is like a little tripod, by the way. That's why the dotted line's there. It's behind the plane of the board. This is like a little tripod, and the negative end of the molecule is here, the positive end of the molecule is here, and it acts just like water does. And if I have other ammonia molecules here, it's going to do the same thing. It's going to create hydrogen bonds. Hydrogen bonds are just one type of dipole-dipole force. They're the strongest type of dipole-dipole force, but there are other polar molecules that create dipole-dipole forces, and we'll need to know about these. Okay, so what factors pertaining to individual gases will affect whether there are significant interparticle forces? And the answer to that is going to be polarity. Okay, if I have polarity, I'm going to have significant interparticle forces, and I'm going to see this. Water vapor would be even further down the list. Their boiling point, water vapor's boiling point is 100 degrees Celsius, right? Not negative 100 degrees, but 100 degrees Celsius. Okay, that would indicate that water particles have much stronger forces of attraction than ammonia does. Okay, everything else on this list is completely nonpolar. There is no electrical distribution within the structure that is going to cause dipole-dipole forces. These are nonpolar, so they have to find another way to stick together. And notice, they're not very good at it, right? Their boiling point is so low that it suggests they don't ever want to turn into a liquid. They don't ever want to turn into a liquid, and we have to get them slowed down really a lot in order to cause that to happen. So here's oxygen, here's liquid nitrogen. I have to get close to negative 200 degrees to turn those into liquids. Okay, so hopefully that makes sense. So now let's consider what happens at extremes. If I have 1 mole of an ideal gas, regardless of temperature or pressure, PV equals nRT, right? Or 1 mole equals PV over RT. This should be the behavior of an ideal gas. I should find out that this relationship holds true. Okay? So let's look at a graph comparing the value of PV over RT, which should always be 1, at, let's see what happens at markedly increased pressures. Okay, so this value should always be 1, right, for an ideal gas. Okay, for an ideal gas, it should always be 1. But let's see what happens if I start increasing the pressure. If I have an ideal gas, it shouldn't matter what the pressure is, should it? I should always have a value of PV over RT equaling 1. Okay, and we've said that things like small molecules like helium and hydrogen, things that are nonpolar, are close to being ideal. Things that are nonpolar are close to being ideal. But let's see what happens if I go and increase the pressure a great amount. Okay? If I increase the pressure a great amount, and let's see what time it is. I'm not going to be able to finish this in the next 7 or 8 minutes and do it justice, so I'm going to hold off on this until next time because I don't want to go through this and then have break and have you forget everything you know about it, okay? So we're going to stop here and we're going to return to that after break, and I'll do a quick review, remind you of that when we get back from break, and then we'll finish this out. It'll take us 15 or 20 minutes to do that. And then we'll need to talk about how we're going to, I'll probably have like some kind of a take-home exercise for you when you come back from break related to gases. Okay, so Jaron, I would recommend that you go over those other lectures. And where were you?
I was in St. George. My brother was supposed to have a football tournament,